Software Engineering 2FA3, Discrete Mathematics with Applications 2. My name is Bill Farmer. We will continue today on the topic of predicate logic. And we're going to start by giving the definition of our version of first-order logic called FOL. We're going to start with the syntax. But before we do that, I have a little question to help you get you thinking about syntax versus semantics. The question is, which sentence in English is syntactically incorrect? I'll give you a moment to think about that. Okay, welcome back. It turns out that all of these sentences are syntactically correct, at least the first four, except for A. A should be they go to Mac. B, C, and D are syntactically correct, but semantically they are not correct. His statements infer that he is angry? No. It should say his statements imply that he's angry. She knows the induction principle that is needed? No. This should be principle spelled like this. And long live the king, you might think that there should be long lives the king, but this is an expression in subjunctive mood in which one is saying we hope the king lives for a long time. So it is syntactically correct, and it's also semantically correct. Okay, so if we have a formal language of a logic, we can think of this as a set of expressions built from a set of symbols. So we have a set of symbols, and these symbols build expressions. From these symbols, we build expressions. And there's four kinds of symbols. There are variables. A variable has a meaning which can vary in an interpretation of the language. So if we're thinking of the language as talking about something, the variable can take on different meanings. So if we have a variable for natural numbers, we can think of that variable could be 2, it could be 5, it could be 6, and so forth. So those are variables. Now a logical constant is a symbol that has the same meaning in an interpretation, and it has the same meaning in every interpretation. So the meaning is completely fixed. A non-logical constant is a symbol whose meaning is fixed in a particular interpretation of a language, but it could have different meanings in different interpretations. And finally, we have punctuation symbols like parentheses. So a signature defines the set of non-logical constants. These things. Constants which have a constant meaning in an interpretation, but they can have different meanings in different interpretations. And so a signature is a set of these non-logical constants, and a signature specifies the expressions of the language. Or another way of thinking about this is once we know what the signature is, we basically know the whole syntax of the language. So in first-order logic, we have signatures that can be defined very simply. We'll start by saying that V here is a set of symbols called variables. So we have some set of symbols called variables. It's countably infinite, which means that we are never going to run out of them. We always have an infinite number of variables that we can choose from. And our signature has three sets: script C, script F, and script P. And these three sets correspond to sets of constants, which are really individual constant symbols, function symbols, and predicate symbols. So constant symbols, function symbols, and predicate symbols. And the function symbols and the predicate symbols, they come with an arity, because these symbols are going to be applied to a certain number of arguments, and that arity tells you how many arguments it can be applied to. So a function symbol is applied to a fixed number of arguments, that's its arity. And often this little superscript here is dropped when we know what it is. And we assume that these sets are all pairwise disjoint. What that means is there's no symbol that occurs in more than one of these sets. And we say our triple sigma, our signature, is finite if each of the sets, script C, script F, and script P are finite. So let's look at some examples of signatures. You can think of signatures as a set of symbols to talk about something. So the first signature is I'm going to call it the EQ signature. This is a language for equality. And in our logic, FOL, equality is built in. So we don't need any special symbols to talk about equality. For that reason, C, F, and P are all the empty set. The next example is sigma ord. This is a language for talking about orders. So what we need is just a relation symbol, less than, and I said relation symbol up here. Actually I should have said predicate symbols. We're using predicate symbols to represent relations. So the difference between a relation and a predicate is a relation is a set of ordered pairs. A predicate is a function that takes, I should say a relation is a set of ordered tuples, and a predicate takes a tuple and returns true or false. So they're essentially the same. So we need a binary predicate, a predicate with arity 2, to represent less than. So that's what this signature is for. It's for talking about strict order. So we can write down statements like this. A is strictly less than B. Okay, so I have a couple more signatures. We have two signatures for NAT, 1 and 2. And in the first one, we don't have any constant symbols, but we have 3 function symbols. This symbol for successor. So like the successor function, successor of 2 is 3. Successor of 100 is 101, and so forth. And we have plus and minus. And a successor function is unary, plus and minus are binary. That's why we have these arities. And we have less than, which is binary as we've seen before. So this is one signature for natural number arithmetic. Here's another one. In this case, we have an infinite number of constants, 0, 1, 2, 3, 4. These are constant symbols, and these are going to denote the natural numbers, and then we have plus and times and less than. And what's interesting about this signature, it is an infinite signature because C is infinite. Okay, so we have one more signature to look at. This is a signature for talking about stacks. And remember, with stacks, we stack up something. So we think of it like this. We stack up things. So there's 2 kinds of individuals we have. We have stacks, and we have the things we stack. And so we need a language for talking about these. And so I'll look at our predicate symbols first. We need a predicate to tell us when an individual is an element, the thing we stack up, and we need one to tell us when we have a stack. And we have functions push. Push puts something else on our stack. And then we have pop. Pop takes off what's on top of the stack and gives us back a stack. And top gives us the top element of the stack. And then we have some constants. We have bottom, that's the starting point, a stack that has nothing on it. We have the air stack. The air stack is a stack that when we have, let's say, the empty stack and we pop it, well, we can't pop the empty stack. There's nothing on it to pop, so we get an air stack. And we have the air element. That's when we try to take the top value of an empty stack. There's no top value, so we get the air element. So this is a signature for talking about abstract stacks of abstract elements. Okay, so now once we have a signature, so let's say we have the signature sigma, now we can define terms. We can define the terms of this signature. And a term is just an expression that denotes an individual. And remember, individuals are whatever you want to talk about. Individuals can be essentially anything depending on what we're concerned about. So a term of sigma is going to be a string of symbols inductively defined by the following statements. So the first says that if x is a variable, x is a term. So every variable is a term. If c is a constant, and that means a constant of our set of constant symbols, then c is a term of sigma. So every variable is a term of sigma. Every constant symbol in c is a term of sigma. And finally, if we have a function symbol of arity n and n terms of sigma, then the application of that function symbol to those n terms is a term of sigma. So there's just three ways of making terms. We have constants, or variables, constants, and function applications. And T sub sigma will be the set of all terms of sigma. Okay, so here's another question. Which of the following is a sigma 1 nat term? Remember, sigma 1 nat, well, we can just go back up and look at it to remind you. Here it is. In C we have 0, and function symbols we have s, plus, and times, and predicate symbols we have less than. Okay, so which of the following is a C1 nat term? Actually, the way I should really change this. The way I was writing this is a term of C1 nat. And we're not using any notational definitions and conventions. We haven't talked about those yet. So take a moment, think about which of these is a C1 nat term. Okay. Okay, well, welcome back. Well, X is certainly one. All variable symbols are terms for every signature. S is not a term. All S is a function symbol. Function symbols need to be applied to things to be terms. This is a term because S is a function symbol of our signature and 0 is a constant symbol. This is not a term because it's not written the right form. It's not a symbol. If it were written like this, then yes, this would be a term. This is not a term because 1 is not a constant symbol of sigma 1 nat. It is a sigma 2 nat, but not sigma 1 nat. And this is not a term at all because this is a predicate symbol. Remember, terms are variables, constants of function application. They're not predicate applications. Now, the interesting thing about the terms, if we take the terms of sigma, we can define this as an inductive set where we have a constructor var, which takes a variable and gives back a term of sigma, con, which takes a constant and gives back a term of sigma. And now, because function symbols take various arities, we need a constructor, one for each function symbol. And if that function symbol has arity n, it takes n terms and gives back a term. So we can define term sigma as an inductive set. And that inductive set, it represents the set of terms of sigma. Okay, so now we know what terms are. Let's move on to formulas. So a formula is an expression, like a term, but remember, terms denote individuals. Formulas denote a Boolean value, either true or false. And so let's say we have a signature, and a formula of this signature is a string of symbols defined inductively by the following 5 statements. We can have equalities. So if we have two terms, we can put them together and form an equality. That is a formula of sigma. If we have a predicate symbol of arity n and n terms of sigma, then the predicate symbol application to the n terms is a formula. Notice predicate applications are formulas, function symbol applications are terms. And now if A is a formula, then we get basically not A is a formula. If A and B are formulas, then A implies B is a formula. And if X is a variable and A is a formula of sigma, then for all X, dot A is a formula. So we have 5 ways of constructing formulas: equalities, predicate applications, negations, implications, and universal quantification. Okay, so let's take a moment. Here's another question. Again, I shouldn't have had this. I should have said formula of, to be consistent, formula of sigma 1 nat. So which of these is a formula of sigma 1 nat? Or which of these is not a formula of sigma 1 nat? I'll give you a moment to think about that. Well, let's go through each of these. This is a function symbol. So this is clearly a term, so it's not a formula. This is okay, because this is a predicate symbol applied to 2 terms. This is an equality. An equality is equals, where on the left-hand side we have a term, and the right-hand side we have a term. This is not a formula. We don't have this symbol. And likewise, this is not, these are formulas, but the whole thing is not a formula because we don't have this symbol. So just B and C are formulas. Now, just the way we define the set of terms of a signature as an inductive set, we can define the set of formulas as an inductive set. So let sigma be I should say we can do this when we have a finite signature. Let sigma be a finite signature of FOL, and we'll define forms of sigma, and we'll have 5 constructors, or 5 kinds of constructors: EQ, EQ, predap, P, for each predicate symbol. Remember, we have only a finite number on neg, implies, and for all. So EQ takes 2 terms and gives back a formula. Predap takes n terms, depending on the arity of the predicate symbol, and gives back a formula. Negation takes 1 formula and gives back a formula. Implies takes 2 formulas, gives back a formula. And for all takes a variable and a formula and gives back a formula. So this inductive set, defined by these 5 groups of constructors, represents the formulas of our signature sigma. Okay, so we would like to make some notational definitions. And these notational definitions are, in this case, you can think of them as abbreviations, but they're a more convenient way of writing down something we want to say. So instead of saying not S equals T, we can say S does not equal T. So this expression really stands for this expression. The one on the right is the official version. The one on the left is the convenient version. So T will stand for a true formula, and one of the truest formulas is for all x, x equals x. And we need F stands for a false formula, not T. And we want to introduce or, and this is called biconditional or logical equivalence. Or is going to be, we have to define it using not and implies. It's going to be not A implies B, and is going to be not the disjunction of not A and not B. Remember, if you remember De Morgan's laws, if we push in the negation into this disjunction, we get not A, and then we flip this and not B, which is equivalent to A and B, is what we have here. And logical equivalence, or this is, like I said, could be called biconditional. It's sometimes called by implication. It's also called if and only if. This is just going to be A implies B and B implies A. And existential quantification, that stands for not for all x, not A. So we're going to freely use these notational definitions because they are convenient. We're also going to use some syntactic conventions. And these are also called notational conventions. And so the first one is we can drop pairs of matching parentheses in a term or formula when there's no resulting ambiguity. So for instance, if we had 0 equals 0, we can write that just as 0 equals 0. The parentheses aren't really necessary. Another thing is, if we had something like this is the second notational convention. If we had something like this, we can write it, because this is a binary predicate symbol, we can write it in an infix format, because that's what people normally do. And the last convention is if we had something like for all x dot for all y dot x is less than y, and I'm using the second convention here, we could write that simply as for all x comma y dot x is less than y. Okay, so we're going to stop here. Next time we're going to talk about variable binders. So I'll see you all then.